But I was talking about how, theoretically, you could have a flat, what we call a flat network. So for example, maybe I've got a switch right here. Could be a switch or a hub or a bridge, doesn't really matter. And I've got some devices connected to it. Let's say 3 devices right now. And I said in this particular case, they're all in one big broadcast domain. Broadcast domain. And I'll say /network, because technically they're all in the same network as well. And with this, really we don't even need any kind of networking layer protocol. There's no routing here. We only have one network. There's really not a need to have a network address. So we could get by with just plain old layer 2 addresses, MAC addresses. Now in reality, you're never going to be able to find a network that works like that because most people use IP. But let's just say theoretically, we don't need any kind of IP. And then we create another network down here. Let's say you've got a couple of people here connected to their own switch. Okay? And these guys are in their own broadcast domain, their own network. And everybody's chugging along nicely. The green people are talking to themselves, the blue people are talking to themselves, but they're not talking to each other. Now we might say, well, I want to join everybody together. I want all 5 of these PCs, these hosts, to be able to intercommunicate with each other. Well, there's a couple of things we could do. We could just stick a connection in here between these 2 switches, and now we've got one giant broadcast domain. But maybe we don't want that for security purposes or whatever. We want these guys to be able to talk, but we want them to be on completely different networks. Hence the need comes in for a router. So we'll put our router right here and connect each switch to that router. So now we've still maintained our division of 2 broadcast domains, because remember I said that each interface in a router terminates its own broadcast domain. But now we can no longer get by with just layer 2 MAC addresses. Remember how I said earlier, now that we have 2 or more independent unique networks, we need to implement the networking layer of the OSI model. So we're going to implement IP, the IP protocol, the Internet protocol. And I said that IP, as part of what it does, assigns each one of these devices, each one of these laptops and PCs here, an address. Now, I mentioned it earlier. Does anybody remember how big that address is as far as how many bits an IP version 4 address is? Some of you may have answered 32 bits, and you'd be right, 32 bits. Now, how big was a MAC address, a layer 2 MAC address? That was 48 bits. And what kind of counting system did we use to represent MAC addresses? We used hexadecimal. So one might think, okay, well with a 32-bit number, are we also going to use hexadecimal? Thank goodness, no. So IP addresses are not represented in hexadecimal, they're represented in what's called dotted decimal. So let's take a look at that real quickly. So if I'm going to make a real simple IP address. Okay, so there's 32 bits. Now, as far as these devices that we put these IP addresses on, like your laptop, your smartphone, a router's interface, it sees it as just a continuous string of 32 bits of some ones and zeros. I put spaces in here because it's easier for us to differentiate it with spaces, But computing devices just see their own address as 32-bit number, and that's it. Now, we as human beings, that number is kind of difficult for us to work with. So we convert it into decimal first. And then we put dots in between each decimal number. So I take each byte, convert that byte into a decimal number, and I ended up with this. And this representation of an IP address is what we call a dotted decimal IP address. Because just like it sounds, it's decimal numbers separated by dots. So an IP address, as a takeaway, 32 bits long. This is how computers and everything else mechanical sees it, but we represent it as a dotted decimal address. Now, I also mentioned that inherent in IP, somewhere in these 32 bits, there's a dividing line. Some of the bits from left to right represent a common network that, one or more hosts live on. And then after that line, the remaining bits represent a unique serial number for that particular host. Now, we're going to see in just a little while, how do we know where that is? Because theoretically, could be right here. I could say, well, all these bits to the left of this green line belong to the network, and these 4 bits belong to this host. Or I could do just the opposite. I could say, why don't we do it like that? This is the network, and these are the hosts. So this is where we need a subnet mask to tell us that information. And we'll get to that in just a moment. So that's why we needed the Internet Protocol, to be able to subdivide networks into multiple discrete independent networks that we could recognize. Also so that routers could recognize them, so routers could route packets from one network to another. Now, IP version 4, as we can see here, is connectionless. In other words, if you open up the RFC for IP, now there's a term I haven't used yet, RFC. What is that? RFC stands for Request for Comments. Request for Comments. Do you remember when I showed you that one slide that showed all the different standards organizations, the IEEE, the Wi-Fi Alliance, and a few others? I said one of them was generally responsible for creating documents that specify layer 3 and above protocols. Do you remember what that organization was that did that? That was the IETF, the Internet Engineering Task Force. Well, when I come up with some new routing protocol, or maybe I don't like IP at all, I want to come up with my own new networking protocol. So I create a white paper that's 200 pages long, and I send it to the IETF. And I say, I would like you to submit this among all of your members, and I'd like to get their feedback. I'd like to get their comments back to see what they think. I'm requesting that paper for comments. That is called an RFC. An RFC is a request for comments. It's a formal definition of how a protocol works. And there's lots of different RFCs out there. So if you ever want to know the nuts and bolts of how some layer 3 or layer 4 or above protocol works, for example, if you want to know how HTTP works, you're curious about all the details of HTTP, go to Google and type in RFC HTTP, and you'll find some RFC document that details how HTTP works. Type in RFC Internet Protocol, and you'll find the RFC for that, which I believe is 791. I think RFC 791 was for the Internet Protocol. Don't quote me on that, though. So if you open up the RFC for the Internet Protocol, nowhere in there does it talk about establishing a connection. Nowhere in there does it say that IP is responsible for determining if the remote destination exists. Nowhere in there does it say, if I send data to you, you need to acknowledge it back to me. That's not the job of IP. That's why we say that IP is connectionless. Now, we've already gotten used to this idea that different protocols that reside at different layers of the OSI model will take this block of data that came from a layer above it and then append some headers to it and then send it down to the layer below. So now what we're going to look at is, what are the various headers that the Internet Protocol adds to data. By the way, you might be looking at this and saying, well, wait a second, Keith, this says IP version 4. Shouldn't we know something about IP version 1 and 2 and 3? No. I mean, if you're curious, you can Google it, but those are like super old, Tyrannosaurus Rex versions of IP. They haven't been around for decades. No one is ever going to expect you to know anything about them. So IP version 4 has been pretty much the standard for the last 30, 40 years, since the mid-1970s, that long. So what does IP4 add to the front of the data that it receives from the transport layer? The first field it adds is the version field, and this is typically the number 4 for IP version 4. For the last decade or so, we've also had IP version 6 come out, and so you could see a number 6 in here. The next field after that is the IP header length, which tells, so if I'm sending data to you, okay, so let's think about this. On your physical layer, on your wire, you're getting voltage 101010. Your NIC card gets that. First thing your NIC card does is translate those voltage spikes into discrete ones and zeros, and then your NIC card says, okay, what protocol am I running? Oh, I'm running Ethernet. Okay, so I know that these first few ones and zeros represent the preamble, and now I know that the next 48 ones and zeros represent a destination MAC address. Is that for me? Now let's say your NIC card says, yep, that's mine, that's for me. Okay, then it goes on to the type field and says, okay, what is this Ethernet header carrying? And there's a number in there. It says, oh, 0x800. This is IP version 4 inside this Ethernet frame. Great. So your NIC card strips off the Ethernet header, revealing the IP header and everything behind it, sends it up to the CPU. Now the CPU, doing whatever it was doing, interrupts itself and starts the internet protocol in your CPU. CPU, first of all, looks at the version field. It says 4. And your CPU says, I'm only configured to recognize IP version 6. I don't know 4. And so it throws away the packet. That could happen 30, 40, 50 years from now, but chances are your CPU will say 4, oh yeah, IP version 4, I totally understand what that is. Then the CPU says, okay, well, how long is the total IP version 4 header going to be before I get to the transport layer header behind it? And that's what the IP header length does. Now you might be wondering, well, isn't the IP header always exactly the same size? Why do we need this? Well, 99% of the time, yes, the IP header is the same size. But the designers of IP said, we're also going to build in some options, some things that go at the end of the IP header, some optional capabilities of IP. 99% of the time, you will never see an IP packet with options in it. But there is potentially an options field there, and you could have multiple options in it. So the size of the IP header is variable depending on whether or not there are options. So that's why we have to know the IP header length. Where does the header actually end? Type of service. This is an 8-bit field, and it's used to indicate the relative priority of a packet. Remember, IP, networking layer, we call those packets. So by default, of this byte, of this 8 bits here, when IP was first developed, they said we're going to use 3 of those bits to indicate the priority of a packet. Now let me ask you this question. If I gave you a 3-bit number, and I said this is going to be represented in binary, 3 binary bits, what is the largest number you could come up with if you only had 3 digits to play with? Well, in binary, that would be 1, 1, 1. And what's that number if you convert to decimal? That's the number 7. So originally, when IP was first invented back in the mid-70s, they said, look, a packet could have a priority of 0 to 7. In this type of service field right here, the first 3 bits are what they call the IP precedence bits. Those are those bits that indicate the priority. By default, every packet that leaves your PC or your smartphone or your tablet has a precedence of 0, the lowest precedence possible. You actually have to configure a device to have it shove a number in there that's somewhat higher than 0. In case you're curious, IP phones by default have a precedence of 101. That is technically the highest precedence you can have of voice or data. Precedence levels of 6 and 7 are reserved for network control traffic, like routing protocols and things like that. Then later on, probably a couple of decades ago, some people said, you know what? We've got 8 bits here. This type of service byte is 8 bits long, and we're only using 3 bits of it. We're wasting it. What about the other 5 bits? So he said, let's still use this to define priority, but instead, let's use 6 out of the 8 bits instead. So those 6 bits, they said, we're going to call those the DSCP bits, the Differentiated Services Code Bits, or Code Point, DSCP. Still the same thing. The field itself still defines the relative priority of a packet. But how you define the priority depends. Are you looking at the first 3 bits or the first 6 bits? And that's all you really need to know for the CCNA. Then we have a total length field. How big is the total packet from the IP header and everything at the end of it? Total length. Now I'm going to put these next 3 fields up here all together: identification, flags, and fragment offset. And what this is used for is that IP within the protocol has the ability to do what's called fragmentation, to take a packet and cut it up into smaller pieces. Let's look at the whiteboard and see why we would ever need to do this. Okay, so I've mentioned how there is more than one protocol that resides at the data link layer of the OSI model. I mentioned the primary one that we are concerned with most of this week is Ethernet, but do you remember any of the other protocols I mentioned that reside at the data link layer? Some of the other ones I mentioned were frame relay, PPP, HDLC, ATM. I didn't mention that, but that's also there. So one thing that differentiates these various layer 2 protocols from each other is the minimum and maximum sizes of frames they can create. Because remember, at the data link layer, we're talking about frames. So the maximum size of a frame is called the MTU, the maximum transmission unit. Okay, so here we've got 3 routers, A, B, and C. And let's say that I've got my host right here connected to that segment and a server right here connected to that segment. Okay, so we will say that these segments with the straight lines are Ethernet, and this is something else. Don't really care what it is. All we know is that it's not Ethernet. Okay, now do you remember I said that the maximum frame size of an Ethernet frame, if you count the data and the headers, a normal Ethernet frame, the maximum size, do you remember what that maximum was? And by the way, that is something you will probably be asked on the CCNA. Do you remember what that was? That was 1,518 bytes, 1588. So here I'll say MTU equals 1518. I think that's why I said 1518. MTU equals 1518. And then down here equals 1518. Now this segment here that's not Ethernet, we don't really care what it is, but what we are concerned with is the MTU on that link. And let's say the MTU here was only 500, meaning the maximum size frame that this particular protocol can carry is 500 bytes. Okay, so we have our host here, and it creates an Ethernet frame. Now you might be wondering, well, how does Ethernet know, when data is coming down from above, how does it know what size of Ethernet frame to create? Really, it's usually the job of the stuff up above. Like, for example, TCP will get a certain size block of data from, IP will get some data from TCP or UDP. an IP will create a packet based on whatever it got from TCP or UDP. And similarly, TCP and UDP, they'll get some data from the application layer. So certain applications will send down the stream very tiny little chunks of data, and other applications will send down the stack really large chunks of data. So at the bottom there, at the data link layer, Ethernet will basically just take what it's been given and wrap that inside of an Ethernet header. Okay? So let's say in this particular case we're using some sort of application that's actually creating maximum sized Ethernet frames. All right, so here's an Ethernet frame right here. 1518 Ethernet frame. Well, router A receives it. Router A's inbound interface has an MTU of 1518. He says, wow, this is pretty big, but I can just barely handle it. Router A looks at all the various different addresses and says, oh, this isn't for me. I need to route it to this other segment. He looks at the MTU of his outbound interface. He says, oh, whew, good thing. This also is 1518. I'll go ahead and forward it. So he forwards it. Now he's going to make some changes to it, but we'll get to that stuff later when we get to routing. So 1518. Okay, now, back when this frame was first created, there was a packet inside of it, an IP packet. Let's use this color right here. So let's say this is our IP packet. And if I was to draw it down here, that IP packet had an identification field. Let's make this larger so you can see it. An ID field of some random number. And what I mean by that is when your CPU creates an IP packet, when it puts an IP header on front of data, every IP header it puts in, it will create a unique random number called the identification field. So let's just say this is 0123A. Okay, so as it went through router A, the IP identification remained as 0123A. That didn't change. Now when router B gets it, router B says, I can't put this frame onto this segment because it's too large. I can only put 500 byte things on here. So router B says, here's what I'm going to do. Let's see, how many, if I'm going to fragment this packet, how many fragments, what's the minimum number of fragments I can create and still put them on here? He says, okay, well, here's what I'm going to do. I'll see 1, 2, 3, and then I'll have to create a small one. So each of these fragments are going to be 500, 500, 500, and then this last one will be 18. Well, actually, can the last one be 18? Can we do that? I guess it depends on what the minimum MTU is, right? Now, if this was an Ethernet segment, we could not create an 18-byte Ethernet frame. That'd be too small. So, but in this case, we'll just say 18 because we don't know what the minimum MTU is of this segment. Now, before router B puts these fragments on here, he says, I have to let the receiver know, the server down here, that all of these were originally part of one big packet. So the way I'm going to do that is I'm going to put the same original ID number inside each one. So the original packet had an ID of 0123A. So that's what I'm going to put inside each one of these packets, these fragments. That will help a little bit. So when the server now gets these, he'll know they were all originally part of one packet that had an ID of 0123A. But we're not done yet. That's the identification field in the IP packet. Now also, within the IP header, there was the flags field. The flags field. What kind of flags do we have? Well, let's actually take a look at an IP packet. Here we have an IP packet. If I expand my IP header, here's the flags right here, and you can see we've got 8 bits of flags, And really only 3 of those bits have actually been defined for anything. The reserved bit, which really isn't used for anything, the don't fragment bit, and the more fragments bit. The more fragments bit. So, how's that going to look on our whiteboard here? So this first one, the flags will be 0. Nope, I'm sorry. The more fragment bit will be set to 1. So in this little fragment here, we're going to go into the IP header. Remember, each of these is a full IP packet with a complete IP header attached. We've taken this one IP packet, cut it up into 4 pieces, and recreated the IP header on all 4 of them. But in order to indicate that they're fragments, we have to do something special. We have to set the identification the same on all of them. And then this first one, we say more fragments equals 1, meaning this is a fragment. There's more to follow. In this next one, more fragments equals 1, and more fragments equals 1. Now this last one, the more fragments field is not going to be set. I'm going to turn that off. So I'll say more fragments equals 0, because there's not any more. That's the last one. That's the last one. Now there's one last piece of this puzzle. So right now we've discussed the identification and the flags field. What about the fragment offset field? The fragment offset field indicates the order of these fragments. Now you might think, oh, okay, well, here's the first one. So the first one's going to go down, then the second, then the... Yes, that is the way router B will transmit them. That is true. The first one will be transmitted, then the second, and then finally this little tiny fragment at the end will be transmitted. And in this particular topology, chances are they would be received at the server in the correct order. But in the real world, IP packets most of the time have lots of different paths they can take, not just one. So in the real world, if I've got a bunch of fragments, some of them might go this way, some of them might go this way, and some of them might go this way, and certain paths are slower than others, other paths might be congested, and so when those fragments arrive at the receiver, they might not be in the correct order anymore. So he might receive this one first, and then this one, this one, this one, so the receiver has to have some way of not only reassembling them back into the correct packet, but in the right order as well. And that's where the fragment offset field comes into play. Not going to go into a lot of details right now for the purposes of time to tell you how that works. I'll just explain it, but I'm not going to whiteboard. The fragment offset field says, if this is a fragment, how many bytes away from the beginning is it? How many bytes away? So for example, this one right here, the fragment offset would be 0 because he's the first fragment. This next one, this is the last one I'm going to do. This one here, fragment offset, would equal 501, right? He'd say, I am 501 bytes away from the beginning. And then you can figure out what these next two would be. So in the event that these arrive out of order, the receiver, by using the identification, the flags, and the fragment offset, can reassemble it back into the correct order, back into the original packet that it looked like before it was fragmented. So that's how those 3 fields work. Then we have the time to live field. When an IP packet is first created, some number is put in here. And it's really up to the application layer to determine that. It's not really IP's job. This is one of those situations where IP provides a blank box and the application has to fill in some number. Now, what's this number used for? Well, it's going to start as a non-zero number. Could be 20, 64, 128. We don't know what it is. But every time that packet gets to a router, the router is going to look at the time to live and decrement it or reduce it by 1. Subtract 1 from it, and then forward it on. And eventually the packet should reach its destination. Now, there could be a situation For example, in the case of a routing loop. A routing loop is where something's wrong with your network and packets are just circling between routers and they're never getting to their destination. It's just going back and forth between routers. In that case, we don't want that to happen forever. We don't want that packet to circle and circle and circle forever. And this is where the time to live can help us. Because let's say the packet enters the routing loop and it has a time to live of 25. Then it gets to this router, 24. This router, 23, and keeps ping-ponging back and forth. Well, eventually, that packet's going to reach a router and it's going to come in with a time to live of 1. That router is going to decrement it to 0, and then the router throws it away. So when a router gets a packet and decrements the time to live to 0, that means this packet's time to live is finished. It can no longer be alive. It must be killed, and it's done. Now, like I said, it's up to the application to determine what the time to live is going to be. So, for example, if we go back to here, this one that I've opened up, notice it's using a time to live of 128 for this particular packet. Then the next field is the protocol field. Just like Ethernet had a type code to indicate what kind of protocol is behind it, IP has a protocol field to indicate what's behind me. Is there a TCP header behind me, an IP header, or a UDP header, something else? And so the protocol field indicates this. Now, there are some protocol numbers that you need to have memorized for your exam and beyond the exam, just when you're doing troubleshooting. So let me write some of the common protocol numbers in here, and you'll definitely want to memorize these. So these are protocol numbers that go inside of the IP packet header. First of all, we got protocol number 1, which is ICMP, the Internet Control Messaging Protocol. Protocol number 2, IGMP, the Internet Group Membership Protocol. This is used in multicast, to assist multicast, IGMP. Some other ones that you're going to need to memorize: 6 for the Transmission Control Protocol, 17 for the User Datagram Protocol, 88 for EIGRP, and 89 for OSPF. So you'll definitely want to have those memorized. Now, if you're using some sort of a CCNA certification guide, if they mention any others, you should probably memorize those as well. But definitely these are the top 6 that you're going to want to have memorized moving forward in life. Then you've got the header checksum. This serves much the same purpose as the FCS does within the Ethernet frame. It detects errors in the IP header. Can't fix them, but it can detect if the IP is messed up in some way. And then you have your source and destination IP addresses, and we've talked about that. It's 32 bits long, and we're going to go into more detail of those coming up. And like I mentioned, there could be some IP options, but probably not. And then you've got your payload. Your payload consisting of whatever the next headers are at the transport layer. So those are all the headers that IP version 4 adds to a packet. Towards the end of next week, when we look at IP version 6, we're going to see that IP version 6 has some of these the same, and some of them are different. So we've already talked about how IP version 4 uses a 32-bit address. I've already talked about how it's a logical address that identifies the network you're sitting on right now, as well as your host identifier. If you pick up your laptop and you move to a new network, you get a new 32-bit address. I've mentioned how IP version 4 addresses are comprised of 4 bytes, what we call here 4 octets, and how we use dotted decimal notation. Nothing new in this slide. Now, why is this up here? Didn't we already see this? The reason why this slide is here is because I want to emphasize that not only can you look at a MAC address, a destination MAC address, and tell whether it's going to a unicast, a multicast, or a broadcast, but IP version 4 IP addresses also come in flavors of unicast, multicast, and broadcast. Okay? We're going to save unicast and broadcast for a little bit, in just a little while. But since I did mention a little bit about multicast, with IP version 4, if you ever see an IP address that starts with 224 up to 239, that range is reserved for multicast. 224 dot anything up to 239 dot anything, those are reserved for multicast. Broadcast addresses a little bit tougher to explain until we get to subnet masks, and we haven't gotten there yet.